Tomographic reconstructions. How can I look into objects without actually opening them? This is possible with tomography. The goal of this video is to give you an intuitive understanding how this is done using the radon transform. So, let's first have a look on a rose where one wants to see the flower petals from the inside. With a computed tomography scanner, short CT scanner, we can reconstruct 2D slices from this rose. Stitching these 2D slices together will then give a 3D volume. For this rose, one can now see how the petals are structured, how they bend, and one could even count the petals without destroying the rose. While this might not have too much practical use, CT scanners are widely used in hospitals to produce detailed images of internal organs like lungs, bones, etc. As tomography is a true lifesaver, let's have a deeper look on it. The first part of this video will show visualizations of this process to give you a good conceptual understanding of this topic and can be seen without math background. The second part of this video will explain the math in detail and you need to know some basics in calculus and geometry. For simplicity, let's only choose a 2D slice for discussion. And, as this rose has quite a complex structure, let's choose an image of the mathematical symbol pi, which consists of only 3 lines. This is just a 2-dimensional object with the shape of a pi that we use as a test object in the so-called object space. Note that every object space related thing in this video is annotated with the color blue. When we now propagate light through this object, for example X-rays, we get the projection for a certain angle. This space is called the projection space and gets the color orange. Depending on the source position, the projection will change. The more projection angles we have, the better the result for the reconstruction. In this case, we choose 360 projections, 1 per degree. Apparently, it makes no difference if we rotate the sample and fix the detector, or rotate the detector around the fixed sample. The result will be the same. To understand these sinograms intuitively, let's go through some simple shapes in the object space. First, we have a small disk close to the center of the object space. Its result is a thick and tube-like sine curve in the sinogram. The intensity of this tube is higher in the middle of the sine curve than on its edges, as less X-rays are absorbed at the edges of the circle. Moving the disk further away from the center, the amplitude of the sine curve increases. Adding a second circle will result in 2 sine curves. Having 2 big circles with different opacities will result in a sinogram where one curve is a bit more opaque than the other one. When the object is not round, the X-ray penetration is not uniform for all angles and therefore the thickness of the curve is varying. With this background knowledge, let's forget for a second that we already know that our object is a pi and try to retrieve this information only by back projecting the measured projections. It's definitely the pi, but somehow a bit blurry. As blurriness comes from low frequencies, can we maybe get a better result by filtering the sinogram by a high-pass filter? Let's try this. We take our sinogram and apply a linear high-pass filter to it, as it is shown in the plot on the right. When we repeat now the procedure for back projecting, in this case the filtered back projection, we get a much more cleaner image that only has some small artifacts. To reduce these stripe artifacts a bit, one can use the Shape-Logan filter, which reduces the high frequencies a bit and therefore gives a better image. As promised in the beginning, we will now come to the mathematical description. Before starting with a more complex back projection, we start with a simpler forward projection for one fixed angle. How can this projection process be described? That is possible with a radon transform. With the coordinate system of x and y, we can define our object space. The object function f of x and y can be used to describe objects in this object space. High values of f mean that there is dense matter, medium values of f correspond to less dense areas, and an f of 0 means no matter. On the other side, we have the projection space that consists of the coordinates s and the angle phi. The detector function is also known as the projection function. These terms can be used interchangeably. To transform from f to p, we need to apply the radon transform, which we now want to build up step by step. First of all, we need a rotated coordinate system with the new coordinates u, s, and the angle phi. As you might have guessed, the integration takes place along the u-axis using the integration element du. In order to sample the whole projection space, we need to integrate over all lines and all angles. To give you an intuition of this process, we first sample all s values for the first angle. The same process is now shown for another angle, just to get more familiar with this principle. To explicitly calculate the value of the integral, we use a rotation matrix to transform from x and y to s and phi. It is a simple matrix multiplication that gives us the new substitutes of x and y, which we can plug into the integral. Du goes from -infinity to infinity. In practice, the object has a limited extent, so it is enough to only integrate over a few hundred pixels. This is now a complete description of the projection. For the back projection, which is nothing but the inverse of it, we would need to invert this integral. Unfortunately, this is a difficult inverse problem, but with some elegant tricks, we will derive the inverse projection next. Lastly, by solving x and y for the variable s, we can describe s by x, y, and phi. This yellow-framed formula is a take-away information from this scene and will be used later. Now we also have enough knowledge to put a coordinate system onto the sinogram that is s on the horizontal axis and phi on the vertical axis. Back to our original question. How can we get from the measured projection P to our object F? And why do we have to filter with this mysterious modulus omega hyperpass filter? For this reconstruction process, we need 4 ingredients. Firstly, understanding of the radon transform, which we just discussed. Secondly, we need the one-dimensional definition of the Fourier transform of the projection function small p, as well as the two-dimensional definition of the Fourier transform of the object function small f. Note that Fourier transform functions have the capital letters p and f. Thirdly, polar coordinates will be used. And lastly, the Fourier slice theorem, which will be proved in the end of this video. Step by step, we will now walk through this derivation for the formula of the filtered back projection. We start with f of x and y on the left side, and when we have a first glance on the result on the right side, we can see indeed that the back projection formula contains the projection function and our famous modulus omega. As already mentioned, one ingredient of our proof is the 2D Fourier transform of the object function f, which transforms x and y into kx and ky. Vice versa, the inverse Fourier transform looks like this. It contains the mathematical expression for f, which is great for us. Coming back to our proof, we can express f now in terms of the Fourier transform. Now we are seeking for a way to apply the Fourier-Slice theorem. In order to do so, we first have to change to polar coordinates and adjust the integration limits accordingly. The current integration limits are going from -infinity to infinity. As we have a Cartesian coordinate system, we have a simple and square-shaped area element that is used to sample the whole K-space. Now we also want to sample the K-space in polar coordinates. In polar coordinates, we can reach any point by the distance r and the angle phi. Having a look again on the area element, we see it is not of constant shape, but increasing for larger radii. From the geometric properties of a circle, we know that it must be r times delta phi. Setting now the integration limits of dr from -infinity to infinity and the integration limits of d phi from 0 to pi, we can move around the area element in this regime. But as this integration boundaries allow also negative radii, the r d phi length must get adjusted to modulus r times d phi to account for negative radii values of r. Now we can also sample the K-space here. And spoiler alert, this modulus r will later become our modulus omega. Now we apply the Fourier-Slice theorem, which will be explained in 2 minutes. When we now remember the radon transform, we can substitute a part of the expression by s. For the last step, we use the definition of the one-dimensional Fourier transform of the detector function small p. The definition of the inverse transform is also shown. Plugging in the expression for the Fourier transformed detector function, we get now our final formula to calculate the original image f in the object space x and y from our projections. This more compact form can be understood as the following instruction. Make the Fourier transform of the detector function, multiply it by modulus omega, calculate the inverse Fourier transform of it, and finally integrate over all angles. To complete the whole picture, this multiplication of modulus omega in the frequency domain is nothing else than applying a high-pass filter. To make this expression even more compact, we define a p tilde, which is the filtered back projection. Finally, we want to bring this in a form that computers can understand. As computers only understand discrete summation and not continuous integration, we sum over all projections. Capital M is here the total amount of projections, and small m goes from 0 to m-1. We have made it! Now we can write a few lines of Python code and make a tomographic reconstruction. And lastly, as promised, we come now to the Fourier-Slice theorem. Here you can see the concept of this theorem. We can follow a path of this diagram to build the reconstruction from the orange projection data P of S and phi at the top left. The procedure is easy. Transforming f of x and y leads to the projection. But this path is one way only. In order to make the reconstruction, we have to go to the frequency domain by applying a 1D Fourier transform. And then we apply the Fourier-Slice theorem, which states the following. A one-dimensional transform of the projection function at the angle phi is exactly the same as the line at angle phi through the two-dimensional Fourier representation of the entire object. With an inverse 2D transform, we can then come back to the original image. Let's walk through this proof. The Fourier-Slice theorem looks like this. The 1D Fourier transform of the detector function on the left and the 2D transform of the object function on the right. Note that we take only one angle, so one slice on both sides. The second line is only a small rewrite of this. We remind ourselves of the formula that was an outcome from the radon transform. As the Fourier slice theorem is valid for any angle, we can choose any angle to make the proof. Without loss of generality, we choose a phi of 0 degrees. It directly follows that s is equal to x and ky is accordingly 0. For our projection, that means that we can simply integrate f of x and y over dy. Looking back on the radon transform, we see that for our angle of 0 degrees, u is equal to y, so du becomes dy. As well, we see that s is indeed equal to x. Later, we will need the Fourier transform of the detector function, so we can already write this down. To familiarize a bit more how slices look in the frequency domain of the object function at the bottom right, let's zoom into it. When changing the angle phi, the slice in the frequency domain will change accordingly. By showing multiple slices, we see that the center of the k-space contains more data than the outer k-space. It is this exact effect that is compensated by using polar coordinates and accordingly the high-pass filter. Finally, we come to the proof. Starting with the 2D Fourier transform of the object function at phi equal to 0 degrees, we plug in the 2D Fourier transform and can discard the ky term as it is 0. Next, we rewrite the integral. Here we can plug in the expression of the detector function. Finally, we rewrite this as the Fourier transform, and we are done proving the Fourier slice theorem for the special case of phi equals 0 degrees. But this also holds for all other angles. Thanks for watching this video, and I hope it gave you a good introduction into the topic of tomography.